My co-authors. Take it back. Okay, right. Thank you. So I said I would like to acknowledge my co-authors, Christy and Jody, and I'll straight away go into this wonderful, enigmatic Naukluft Thrust. So what has amazed me in Namibia, in the Naukluft Thrust, is the fact that when you look at most Pan-African belts in Southern Africa and in East Africa, most of the large thrusts are carried by limestones. But in Namibia, the Naukluft has this so-called soil-dolomite, which is basically a cataclasite. And if I'll be able to show you here with my laser pointer. So here is the soil-dolomite, and it's really very straight and consistent over long distances. And the lithology in the thrust is actually dolomite. And so we can see from the collision of Congo and Kalahari, we see the two continents coming together, and that causes uplift and probably gave us enough height to be able to release this thrust by gravitational thrust from where it was over here, coming down into the Naukluft. Now, the biggest problem is that if you look at other thrusts in Central Africa, on the Copper Belt, for example, we have got evaporites and limestones transporting huge thrust over long distances. But in the Naukluft, it's a dolomite. And that has been really a big problem. Okay, just to summarize for those who are not aware of the Damara, I'm sure everybody here does know that. So basically, it's almost 400 kilometer wide, northeast trending, intracontinental arm, and about 150 kilometer wide north-south trending coastal arm called the Kaoko. So these arms, they appear to meet along the southwestern lobe of the Cameroon Inland. But our main concern today is how this thrust was transported from here up to here. So we have to explain this somehow by mechanical aspects. When we look at thrust sheets in many areas, they are always carried by rocks that are able to allow the rock which is sitting on top to move. But how does a dolomite do that? Because dolomite is quite a very hard lithology, which deforms by brittle deformation. So Windhoek is somewhere here, and we suspect that this thing came from anywhere around here, coming all the way there. And that's quite a large displacement. And Chris, in his map, had in his thesis suggests 78 kilometers. Other authors have suggested that the distance may even be longer. And the work of Kohn and Martin also showed that there is very consistent thrusting on this so-called soil-dolomite. And how was that happening? Mechanically, it's still enigmatic. And their map shows the fact that during the thrusting, we do see that areas where the topographical highs are compensated by depth. So that would also imply that you need to have a kind of mechanism that allows the thrust to actually come up like a pebble bouncing off the water. So this is our thrust again. So this is the map, which is after Chris, 1978. So what I would like to show you is that the whole thrust from bottom up to the top was carried as a single package over time. So it was not a single event. It must have happened over time. If it was a limestone or evaporite thrust, probably we could have said that it could have happened over time. So emplacement from north to south onto the southern foreland. And then we find that these Swakop group lithologies are maintained they are maintained in quite very good stratigraphic order. People are able to come up with beautiful stratigraphies. And so that calls for big questions. So what we have seen so far is that the soil dolomite, as we saw it, actually is a fault rock in itself that is being formed by dolomitization taking place as it is being moved. So the dolomitization is not a single event. It is taking place over time. We see exogenous clasts in the soil dolomite, and these clasts, I've got also some pictures that I'll show you, are found in different places along the Naukluft Thrust itself, telling us that this process was happening in this huge area of the Naukluft of about 60 kilometers from north to south. So here's one of my favorite outcrops. I think that's Rowe Miller there walking up to the thrust. And here we see a very clean fault line. And above this, we do see this dolomite and the limestone, the Nama limestone below. And the deformation we've seen here has given us some glimpses into what might have been happening. For example, we do see cataclastic textures, and we do see textures that show clearly ductile deformation that is associated with fluids. So this material must have been very ductile when it was moving. And we do see plain cataclasite. So how did that happen? Here we do see a little bit of folding in the cataclasite, and here are some of these exogenous material which are found within the fault itself, the thrust. So as I was saying, limestones are generally more ductile, and these have been documented around the world, in the Alps, in the frontal ranges, in the Canadian Rockies, and in the Lufilian Arc in the Central Copper Belt. So what we find in Namibia is really something very unique. And dolomite as a lithology is much, much more difficult to deform in a plastic manner. And hence, its presence in the thrust itself and involving some brittle deformation, and also in some cases, some ductile deformation, requires some explanation to do. Then the other thing we see is that most of the dolomites we find in the Naukluft Thrust, they maintain a very high level of preservation with very minor brittle deformation. You do see some jointing, a bit of folding, but the whole package is preserved. So what that tells us is that the transporting basal thrust was able to carry this as one contiguous unit. These are some of the textures we do find. And something interesting is that from the fault into the hanging wall, we do see injectites. These are fluids that have been injected into the hanging wall from the basal soil dolomite. So that tells us that there must have been some fluidization during the thrusting event, and therefore we should have episodes of high fluid pressures taking place. Here's another example with a breccia overprinted by ductile fabrics. So this can only come that you had brecciation, and then you had an event where you had fluid passing through this unit in a very, very, very rapid manner, very quick seismic events. Here, a few more textures, breccias, showing you that in actual fact, in this soil dolomite, we have got two kind of modes of transportation, ductile and brittle. So we would suspect the brittle to start first as the initiation of the thrust, and then the ductile fabrics, and then the thrust stops. And then another episode comes, giving us in the whole a complete clear image of what is taking place. So what I would like to say is that the soil dolomite is a problem which we think maybe we may not be able to solve completely, but when you look at the thickness of the thrust, the thrust package is very big compared to other thrust packages around the world. And then the basal thrust is a dolomite, the so-called soil dolomite. It's not a limestone. So in general, the thicker the cataclasite, the lower the displacement per movement over time. And therefore, this large displacement we see over the Naukluft if it was carried throughout with the soil dolomite, it should imply that we had a substantial amount of time in carrying it from the central Damararan belt to the Naukluft where it is currently. All right, and then this suggests episodic movement. And then it also suggests that we had dolomitization taking place up to 70 to 75% of the lithology. And each time this happened, the first initiation of the thrust would be a brittle event. That brittle event would then be overprinted by a ductile event through fluidization of the thrust. Okay, so we needed very high vapor pressures in order for movement to take place over longer distances. And we have some textures telling us that this actually happened. And then we would have to have this fluidized mash, which would solidify after a while. And then microforts would be taking place over time. And these ductile phases would always allow for brittle phases after crystallization of the ductile phase. Okay, here are a few textures of the footwall calc mylonites, which we see that these suffered ductile deformation, whereas the cataclysite itself suffered both brittle and ductile deformation. Okay, I'll pass over that. And then we did look at some shear fabrics, and we find two main directions. We find shear fabrics of northeast over southwest, this one, and then with the second one, which overprints the first one, is northwest over southeast, so which is this one. So this again gives us a very good idea that what we are seeing in the Naukluft is not a single thrust movement, but several episodic movements over time. This kind of cartoon that I created kind of summarizes what may be happening. So we have formation of calc mylonites, and then when we have high fluid pressures, we break the pressures and we move the thrust. And again, crystallization happens, we break the pressures and move the thrust, and this happens over time. Okay, so this cartoon is from the paper by Christie et al. And here it's clearly shown how on microscale this carbonate mineral coating on the cataclysite was happening during these earthquakes. And this diagram on the right-hand side, my right-hand side, I hope it's your right-hand side as well, it shows us that we can see some angular fragments, and then we do see some rounded fragments due to the chemical reaction taking place. And this is happening because we have oxide particles in a fluid of CO2 and H2O. And this should actually tell us that the thrust was actually as a result of these high fluid pressures of SiO2, CO2 rich fluid. At the same time, we should have had enough shear heating to bring temperatures to much higher, because when you look at the metamorphic grade of the thrust packages, it's very, very, very low. But the heat required to produce these fluidization events in the thrust is quite high. So we must have had exothermal reactions taking place, producing these high heat, enabling CO2, H2O fluids to actually lubricate the thrust and then move the thrust, whereas the packages on top of the thrust would remain completely unmetamorphosed. Okay, so here is just to show you that it's impossible to have the Naukluft thrust in its current position if it were to be done without special mechanical aspects attached to it. And this statement probably would summarize some of and probably answer some of the questions that we are actually looking at. The fact that this thrust contains a cataclystic dolomite fault, and this featured dolomite requires us to actually come back and think about how it actually formed. So this is known as the gritty dolomite. And it is interpreted as a signature of core seismic carbonate dissociation and subsequent fluid block interaction. So we needed these faults taking place, earthquakes taking place over time. And then these packages that we call the Naukluft Thrust package would be moving from north to south. Okay, so this is probably one of the areas where we have actually looked at this fault in very great detail. This comes from the paper by Christie et al., which we published in 2012. What you see here is the fact that at the end of the termination of these thrusts, because beyond the Naukluft, we don't see as good evidence of thrusting as before it. We do see what we probably would call the double dolomite. You have one thrust and a second thrust, or a smaller thrust and another thrust. So this would happen if during propagation of these thrusts, we have a competent rock that has already formed, allowing the new thrust to actually open up and produce two thrusts to release the stress and strain in the fault line. Okay, I think I'm going to end my talk there because my time is almost over. I'd like to say what we see in the Greek dolomite is that the contact and cataclysite pressures, they suggest high differential stresses and high strain rates. So these can only happen if we've got proper earthquakes taking place. Okay, so this is supported by fine fabrics observed in the soil dolomite itself. And these should have occurred further as each movement was taking place after each hydraulic event to allow for the formation of the cataclysite in the fluid medium. So in order for this to happen, the limestone must have been dominant rheology, and dolomitization must be a late feature. This was also suggested by Miller in his book in 1983, The Evolution of the Damara Belt. And we can see this kind of episodic movement when we look at several orogenies where we do have thrusts. And what we see is that these thrusts don't take place in one go. They take place in several episodes. And this is recorded in the geological history. And I don't see why it should be different for the Naukluft. And we can see it in the Archean, we can see it in the Paleoproterozoic, we see it in the Neoproterozoic, beginning of the Neoproterozoic, and we see it in the Naukluft. I would like to thank all of you for listening. So finally, we have a kudu, which represents earthquakes, and we have a tortoise, which represents slow movement before the onset of a high fluid pressure event. Thank you.